Welcome to today's fundamental analysis seminar. Today we are very happy to invite Dr. Fengxiang He from the University of Edinburgh to give us a talk. He will talk about building up deep learning theory, perspective, optimization, and the loss landscape. Dr. He is a lecturer at the School of Informatics, University of Edinburgh. His research is in trustworthy AI, particularly deep learning theory and explainability, theory of decentralized learning, privacy in machine learning, symmetry in machine learning, learning theory in game theoretical problems, and their applications in economics. He's an Area Chair of ICML, NeurIPS, UAI, AISTATS, and ACML. So let's welcome Dr. He to give us this talk. Thanks.
Thank you so much for the invitation. I'm very happy to get to give you this seminar. And the topic today is building up deep learning theory. And I will talk about my research and the research landscape in optimization and loss landscape. So, deep learning enables the recent automation revolution, and we have seen its progress in computer vision, natural language processing, audio processing, and finance. Some of the application domains are security critical, like autonomous vehicles, medical diagnosis, and a very small algorithmic error in these areas can lead to fatal disasters like this crash. And the current success of deep learning is largely built on experiments, but without solid theoretical guarantee. So why do we have confidence to use deep learning in these areas? And a major problem now is a conflict between theory and experiments. We know that deep learning models are so over-parameterized, but empirically, we found deep learning models have very excellent performance. In other words, the theoretical case of dimensionality doesn't happen. And the beginning of the recent story started in 2017 when John and his co-authors conducted systematic experiments. They found neural networks can almost perfectly fit the training data, even when the training labels are random. And here are the results. The blue points are for true labels, and all other points are for random labels. And after sufficiently long training time, we found the training loss convert to 0. But the test error is around 0.9 when the labels are random. And this data set is CIFAR 10. There are 10 classes. So a random guess will have an error of 0.9. It means that when the labels are random, there is no knowledge has been learned by the deep learning model, even if the training loss has converted to 0. After that, Kawaguchi and his co-authors in 2017 summarized some promising directions and open problems, such as understanding the large capacity, the complexity of neural networks, the algorithmic stability, and the robustness of deep learning, also the geometry around the local minimum. The first step will be exploring existing theoretical tools like VC dimension. Harvey and his authors in 2017 proved some generalization bounds by VC dimension, a conventional tool of e-learning theory. And they follow a roadmap of 2 steps. First step is proving upper bound for the VC dimension, and then prove upper bound for generalization error. And they found that the VC dimension is of order WL log W, where W and L are width and depth of the neural networks. And also they proved the bound of order WU, where U is the number of hidden units. And all WL and U are very large, extremely large. Sorry. The second step is for generalization bound. It's of order H over N. H is the DC dimension, N is the training sample size. To come back to the DC dimensions upper bound, we found both bounds will be significantly larger than training sample size. In other words, this generalization bound will be vectors. And if we use 0, 1 loss for training neural networks, we will find the generalization bound is will be significantly larger than 1, a trivial bound. So this bound can be vectors. Another choice is random high complexity. Golovich and his courses in 2017 proved some bounds via random high complexity, but their bound depends on the norm of the weight matrix in each layer, and also depends on the network depth. In other words, these bounds also explicitly depends on the model size. Afterwards, Bartlett and his courses proved another generalization bound via the spectral norm of the weight matrices. This will be the first one that does not explicitly rely on the network size. Nishaba and his courses concurrently and independently prove very similar results. The two bounds are almost the same one, but they use another approach. They prove a perturbation bound when inserting Gaussian noise into the network parameters, and then use Peck-Bayesian approach to upper bound the generalization error. And this the two bounds suggest that the generalization error depends on the spectral norm of the neural networks. And the spectral norm is the functional norm of the neural network. So it means that if the mapping represented by the neural network is more significant, is more the generalization error will be larger. So we can penalize the spectral norm to as a regularizer to boost the performance of neural networks, and it has been verified by experiments in a work by Miyazawa and his courses. They use the spectral norm as a regularizer in GANs. Another choice of norm would be Victor norm. Liang and his courses prove that most Euro norms can be controlled by Victor norm. It's like an umbrella of many existing norm-based complexity measures. And we also use this approach to prove a bound for RNN. To come back to all of these results, we hope to prove a norm-based complexity of neural networks, and we hope the measure is relatively small, is reasonably small, so that the generalization error of deep learning can be reasonably good. But it sounds like we hope to prove the over-parameterized model has a reasonably small complexity, but we can prove universal approximation theorem of neural networks. It means that neural networks can approximate any continuous function. It's firstly proved by Sabenko, Funahashi, and Hornig and his courses in 1989. The three groups of authors prove the first version of universal approximation theorem. Afterwards, Hornig proved that even one hidden layer neural networks had such property. Lu and his courses found infinitely wide networks can also have universal approximation ability, and Allen and approved have such property to approximate any sequence, and deep neural networks are proved to have a universal approximation ability in terms of distribution, approximating distribution. So all of these results suggest that the capacity of the neural networks are very large, extremely large. So, and if we still hope to prove they have relatively small complexity, it sounds like we hope to build a bicycle and hope to use it to travel to the moon. And any other choice? The vision is we probably can look at the optimizer, because the whole hypothesis space of deep learning is very huge, and it has been indirectly proved by the universal approximation theorems, but the optimizer would probably explore a part of the whole hypothesis space. In other words, the effective hypothesis space will be significantly smaller than the whole space. And some authors have noticed that a paper by Porter and his courses highlighted that the stochastic optimizer used in deep learning is probably a regularizer in controlling the complexity. And in 2017 proposed to model the stochastic gradient descent by some dynamic systems. And his courses in 2017 proposed to model SGD by stochastic differential equation. And the trajectory of such equation expresses the trajectory of the optimizer. And well, if we suppose SGD is initialized by some distribution, so the optimization process is like a Bayesian inference process. We initialize the model parameter by a distribution, and after every with update, the distribution is shifted to another. And after sufficiently long time, if the distribution, if the process can convert to a steady distribution, this steady distribution characterizes the distribution of the learned neural networks. So it looks like a Bayesian inference process. It's quite interesting because previously we hoped to formulate Bayesian inference as an optimization problem. We found the stochastic optimization is actually a Bayesian inference. So in the rest of this talk, I hope to introduce two of my works in more technical details. And well, the first one is about the dynamic of generalization of SGD. So theoretically, we prove the generalization bound, and it does not rely on the network size. And we hope to this generalization bound suggests some properties which is later empirically verified. We model SGD by a diffusion equation and a stochastic process, and later calculate the steady distribution and then prove generalization bound. This is the stochastic process of SGD. Here, theta t is a parameter of the neural network in time step t, and delta theta t is the weight difference with update in time step t. G theta is the gradient and eta is the step size. S is the batch size, and here W, delta W is a Gaussian noise. So this term is the Brownian motion. So it looks like the motion of an ink molecule in a river. This term characterizes the motion of the river of the water, and the Brownian motion is the diffusion of ink in the river. We prove that the static distribution of this stochastic differential equation, it looks like this formula, and the sigma characterizes the magnitude of the randomness, and is governed by this equation. Here, A is expresses the local geometry around the global minimum, or the local minimum that of the learned neural network. And this assumption is indirectly realized using some popular neural architecture. And finally, we get a basic generalization bound for SGD. And we found here that the determinant of A relies on the network size, and we later go to study the tightness of the bound. And well, we found the only term relies on network size is the determinant of Hassan A. So, but the determinant of Hassan has been studied in some empirical works like Sagan and his authors in 2016 found a bulk of eigenvalues centered close to zero. So it suggests that the determinant of Hassan will be quite small. And it was later verified in another empirical work by Papin in 2018. They found in quite many cases, many eigenvalues around zero. So later we found some hypotheses like the negative correlation between generalisability and batch size, the positive correlation with learning rate, and negative correlation with the weighted ratio. We trained 1,600 models and conducted a Spearman-Rank-Holder correlation test. It's the result area points in the neural networks. X is for batch size and Y is for test accuracy. And this visualization indirectly suggests the correlation. Similarly, it's another correlation. The correlation between the ratio and generalizability. The other is the second case. Also, the hypothesis, the p-value of the hypothesis testing, the testing between ratio and generalizability. So all of these, the previous results are for the via SDE, and for solving a differential equation, we need the boundary condition, and we need the derivative of the differential equation, and all of these values are determined by the geometry of the loss surface. So the next step is looking at the loss surface, the geometry and algebra of the loss surface. Well, there was a debate about the role of nonlinearity on shaping the loss landscape. Kawaguchi in 2016, Lu and Kawaguchi later in 2017 suggest that linear networks do not have any spurious local minimum. Here, linear networks means the neural networks which does not have any nonlinear activation functions. And later, the community suggests that nonlinear network probably inherits some property. Inherit this property, someone proved no. Yun and his authors in 2019 proved that the nonlinearity in neural networks bring in infinitely many suboptimal local minimum. But their results are under conditions of one hidden layer, a square loss, one-dimensional output, and two-piece linear activators. And my work extend the conditions to arbitrary depths, arbitrary differentiable loss, arbitrary damage of output, any piecewise linear activations. Also, the geometry of loss surface, when the neural networks is a ReLU network, that all activation functions are ReLU functions. Saudry and Hopper proved that the loss landscape is partitioned into many smooth and multilinear cells. The boundary between two cells is determined by the turning point in the ReLU function. And if and the linear part of ReLU function corresponds to the interior of the cell. So intuitively, if the information flows through the neural networks, all in the linear part of the ReLU functions, the corresponding part areas in the loss surface will be the interior of the cell. But if the information flow jumps through a turning point in the activation function, the point on the loss surface will jump through the boundary of two cells. And we are going to study some sophisticated geometry of the cells partition in the loss landscape. And okay. We prove that every local minimum within a cell is globally minimal. And it suggests that the geometry within a cell is like a linear networks. And within a cell, we put all local minima on a local minimum value. All of these local minima are connected with each other, and all the local minima are from one equivalence class. And we can construct an equivalence mapping for the equivalence class, and the mapping and the equivalence mapping induced a quotient space, and I will give an example later. And this property explains an empirical finding by Gary Pov and Drexler in 2018. They call the property as mode connectivity. The original statement is like the minima found by gradient-based methods are connected by a path in the parameter space with almost a constant empirical risk. But we prove that it's not almost a constant empirical risk. It's just exactly the same empirical risk. Now we give a simplified case to show the proof sketch. And for a general case, all these can find in my paper. So for two-layer neural networks, phi with leaky ReLU activation sigma, its output given on sample point x can be represented as W2 sigma W1 x. Here x is the input, W1 is the weight matrix of the first layer, sigma is the leaky ReLU function, and W2 is the weight of the second layer. Now so because sigma is the leaky ReLU function, it's a two-piece linear function. When x is larger than when W1x is equal to or larger than 0, the this leaky value function will have slope of s plus, so it equals s plus w1x. Otherwise, it's s minus w1x. And for the brevity, we define a function at. It equals s plus when t is equal to or larger than 0. Otherwise, it's s minus. So it's like identity function, identification function. It means that it defines it transmits the leaky value function into a stepping function.
Excuse me. In the second bullet point where you define sigma of W1x, should the conditions be x greater than or equal to 0, or should it say W1x?
Sorry, it's W1x.
Right, thank you.
All right. So sigma W1x equals A W1x W1x. Then we can calculate, so the W2 sigma W1x equals W2 diagonal A W1x W1x. Here, the diagonal function, the output of this diagonal function is the diagonal matrix, and all diagonal entries are AW1x, and all other entries are 0. And later we can exchange the position of W2 and the diagonal matrix. It becomes AW1x and that diagonal W2, because AW1x is the constant value. So we can exchange the position of W2 and W1x. And here, for the simplicity, we assume the second layer is one-dimensional layer. It's a one-dimensional layer. But for a vector W2, we can also we have a similar result, but here we just hope to showcase its proof. Later, we exchange the position of AW1x and the diagonal matrix W2, W1. So it becomes the transpose of vector diagonal W2, W1, and AW1x, the tensor product of AW1x and x. So look at this term. The second term, so within a cell, the second term doesn't rely on W1 because this AW1x is a constant within any cell. So the second term doesn't rely on the network parameter, but only on the input x. So we can rewrite the second term as hat x. So we reparameterize the second term into x hat. Then look at the first term. The first term only relies on W1 and W2. So we can rewrite the first term as W hat. So via the calculation, we reparameterize the neural network into a new one, W hat, X hat is a linear model. So within a cell, we can reparameterize the neural network into a linear model. And this linear model, W hat, X hat, is convex actually within the cell. So if this linear model has a local minimum, it must be a global minimum within the cell. So, but this original model, the original neural network is not convex. It probably have many local minima within the cell. So the calculation here actually constructs a quotient mapping, an equivalent. It constructs a mapping from all the local minima of the original neural networks into the single, the unique local minimum of the linear model. So the second step is that because all the calculation here are equation, so we actually prove that all the local minima of these original neural networks have the same training loss of the global minimum of the linear model. So we and all the calculations here are continuous. So we actually prove that all the local minima of the original neural networks are connected, are continuous, because all the calculations here are continuous. So we prove that within a cell, all the local minimum are connected. They have the same training loss, and they are actually from one equivalence class. And we actually construct the quotient mapping. And well, and through this way, we actually construct an algebraic structure of neural networks. And so another approach, the next step will be understanding the optimization behavior within the cell, and the behavior jump from one cell to the next. So, and these are future works, and these are some studies some works that I'm working on. And well, thank you so much. It is my talk. Do you have any questions?
Can I just clarify, the cells are defined by the combinations of choices of signs of all the
Yes.
value functions. So there are two to the whatever the number of
Yeah.
So there are an awful lot of cells.
Yeah.
Far more than one could reasonably compute in practice.
Well, we actually can compute the cell, and even if the number of the cells will be extremely large and will be near exponentially exponential in terms of the depth of neural networks. And it's actually another area in deep learning theory. We usually put the number as linear region counting. And some groups in Germany, they found that the linear region counting actually characterizes the expressiveness of neural networks. And actually, when the linear region counting grows, neural networks probably have better approximation ability. And some groups in Maryland has actually visualized the cell. They found that they empirically visualize the linear cell, the multilinear cell on the loss landscape.
Thank you.
No problem.
Can you go back to that slide where you had that measure with sigma inverse? You had that measure with the sigma inverse written, right? One of the slides. Sigma inverse thing.
Sorry, I didn't. What that's the measure of what?
You had a measure, right? The convergence measure of your stochastic differential equation was some sigma inverse. Yeah, okay, yeah. So you see on scale that this is the mixing distribution of stochastic gradient descent. Not possible.
Oh,
I can't believe this is possible. Stochastic gradient descent will definitely produce atomic layers. This is too smooth a measure. I don't think this is possibly an answer. There's some strange assumption you're making about the neural network, which is making this something is happening wrong here. I think this is. And if you do, is there a stochastic differential equation baseline you have for which you can prove this is the measure convergence? Do you have that stochastic differential equation?
In this differential equation.
But this is not a stochastic differential equation.
Yeah, right.
So do you have an explicit stochastic differential equation whose mixing measure is exactly that?
Well, yeah, it's delta theta t, and if you rewrite it as d theta t, and here and rewrite it as dp, we
Yes.
It has been a differential equation.
And can you prove that the mixing measure of that stochastic differential equation is this measure?
It's not proved by me. It's classical results is the Fokker-Planck equation, and the initial distribution is the Gaussian distribution. And so if the neural network is initialized by a Gaussian distribution, the result is the steady distribution is like that.
I can give you explicit neural network where the answer is different.
So why?
It is not the answer. I can give explicit depth to neural networks where I can tell you the stochastic differential equation which probably approximates SDD. That stochastic differential's mixing measure is not this measure. I can give you explicit neural net loss function. If we go to the
What's the result? What's the result?
there's something going on here which is
So your point is like-
either there's a strange assumption which is making this the mixing measure, or there is no proof that this is the mixing measure that's me. Because I can give you explicit neural networks with a stochastic differential depth to neural network. Take any depth to neural network with a regularizer, where I can prove that the stochastic differential equation corresponding to this same process that you have, the mixing measure is not this.
So it's like what?
It's a Gibbs measure.
Sorry?
It's the Gibbs measure of the loss function, is a mixing measure. It's probably true. There's something going on here which is making this down. I mean, there's some strange assumption which is making the, I think this A thing that you're assuming is A is an assumption, right?
No, it's not an assumption.
You're assuming the risk looks like this, right?
Yes, yeah.
So this is an assumption.
Yes, right.
Yeah, so this assumption, my claim is that this assumption is too strong to be true in the real world.
Well,
And this is driving the answer.
so if you could say the local geometry is more complex,
Yes, so
then the smooth one is actually can be characterized by A.
so R of theta is the full risk function, right? So I will take R of theta as the risk function of a depth to neural network.
So if the geometry is very complex, A can be complex. A
No,
can characterize the
it may not
complex.
even look like perfect. There's no reason for the risk of the neural net to look like this.
So just suppose that A is not determinant in positive determinants. So it is,
No, it doesn't even have to be a quadratic function of theta. R of theta is the risk of the neural network, right? So I will take the actual risk of the neural network, which is the full loss function. Then it does not look like this at all.
so it means that the neural network has many local minimum,
Yeah, I will take the
Right.
full risk function.
but it will converge to one of the local minimum.
Yeah, sure.
So you can transmit the 0 point to the converged local minimum and study the local geometry of this converged local minimum, right?
But those are unprovable assumptions. All of them are.
This is the first term
Yeah, so
in the local expansion.
which is very
of
hard to
RFP
prove this thing.
round the global
No,
minimum.
no, I know that there are quite many local minimum, but the neural network will.
But if you look at the full risk function
Uh-huh.
and write the same SD that you have,
Well, the logic is that we assume the neural network will converge to one of the local minimum and then re-parameterize.
yeah, so
the
that's a
local
strong,
maximum.
that's what I'm saying. You're making a very strong assumption about the local structure to make a proof work. But the
What's the assumption?
actual measure can be very different than this. So
It's just
the
that those guess that we just assume that the neural network is one of the local.
so you're making an approximation, a very strong approximation here.
Why is it wrong?
Because the actual risk function looks a completely different function of theta. It does not have this.
Yes, I know that. You don't have to say that there are quite many local minimum.
No, I don't care about the local. I'm saying the full function. Look at the full function of theta. It's a way more complicated function of theta than this, right? The full risk function.
About the local geometry. The
Yeah,
local
then that's
of one
but
of.
that's an approximation. And that approximation you have done is very strong. So you are approximating the full risk around the local minima by a quadratic function. And that approximation, I claim, is way too strong.
So which one do you think is reasonably?
The full risk function. I will
Okay.
write the full risk function.
Okay,
in
well,
neural
I will explain that. If you that a full training, the full loss function, right?
Yes,
And there are quite many local minimum.
sure.
So it's like a mixture of such like kind of this geometry, right?
No.
No.
No,
It
this is,
Do you think it's too strong locally?
yeah, this is very strong an assumption. That's why you're getting an answer which is,
It is too strong if we look local.
yeah, even locally it's a strong assumption.
Why?
Because your measure is, one way to see why it's a strong assumption is you're getting a measure which looks very different from what you probably see for the full measure. If I take the full risk function and I write the stochastic differential equation.
So if we look at the loss function locally, why we consider the global property of the lossless?
I think that the point here is when you do the proof, you utilize the size of your local region. So if you do local approximation with that, you have to have a local region where it works.
Yeah,
You
right.
use that in your proof. If you use that, and then if you include that, then it could work. But then if you don't use that, or if you don't change your A, when you change where you are in your space, then
Well,
So my point is, if I make no approximations about R of theta, I can write down neural net risk functions R of theta, which is exact with no approximations, and I will rerun the full proof of this stochastic differential equation for that full risk function. I can prove what is the mixing measure for the SE. That mixing measure will probably be the Gibbs measure of the loss function and not this mixing measure. And the Gibbs measure of the loss function is very different from this measure. And that difference is so freaking huge, I think it is a sign that you're working in an approximation which is unrealistic.
Is this the second order approximation?
See, you can take any smooth function and truncate it to the second term. But then what is the error you have accumulated of all the higher order Taylor terms?
but it's not about
Yes,
the
so
mix.
this is not including those higher order.
Yeah, and that cost is way too high, is what I'm claiming. You just build the entire neural network to a linear function essentially. Now this is a linear network. This is not even a neural network.
But this like taking this risk measure assumes that you have like entered all the first order errors, and then you are trying to find some second
That will
order.
create more problems
If
for
we
you.
think it's too small, we can prove that we actually can have effectively that the upper bound of the geometry. So
See, let me take another way to see why this is the wrong assumption. And it's
the
to say,
point is to capture the sharpness of the local minimum.
no, the point is,
If you think it's not so smooth, we can construct a smooth local minimum, but it's sharper than the actual one.
but every time you do that approximation, your approximation is valid even inside some open ball around your local minimum.
Yes.
Now, if it's valid in the open ball around the local minima, you will have to prove that the stochastic differential equation, which is initialized inside the token ball, stays within the token ball. And that kind of confinement proving is nearly impossible.
But it's not about the process, it's just about the converged one, the converged point.
Sure, but the convergence point depends on your starting point. You have to make assumption of where you started from. So that is why I'm saying this answer is,
Okay, I know you.
this is way off. This mixing measure that you have is way off the real.
So,
It is not going to happen like this.
imagine that the optimizer has been besides a local minimum, right? Just beside this one, and well, and then it's a possible new initialized point, and from that point to convert to the local minimum, and then makes this.
No, because then you will have to prove that the entire stochastic differential equation's path remains confined inside the open ball where the quadratic approximation holds. And that is nearly impossible. You run into that other problem. Basically, your result, as far as I can understand, applies only to without activation model. You have to remove all the activations of the neural network so that it becomes a linear function. Now you take a square loss of the linear function, you're back to a Gaussian problem. And then you get this answer. This is, I cannot believe this is an answer for a neural network. This is not an answer for the neural network. This is an answer for
Basically, like linear regression?
yeah, this is linear regression. This is not neural network. It's
I think that's correct. Up to the point where you confine your function to each particular cell, leaky revenue network we use as the example. And also, it's locally linear within each cell. When you change from one cell to another, you change linear function. So in each cell, it's linear, and this one, and when you put it across, this is exactly correct.
But then you'll have to, then we will land up with the problem of showing that the stochastic differential equation you're operating with remains confined within that cell to the entire dynamics.
Yeah.
And that is nearly impossible to do.
Yes, and indeed, it won't be true.
Yeah, probably.
Okay, if you suggest that it's globally correct, it's linear regression, but we don't claim that it doesn't need global correctness. It just needs to,
But if,
well, even if you think it's not locally correct, we hope we can construct a locally form the
But then how will you-
umbrella of the true
but how
local
will,
minimum.
but in that case, how will you prove that the stochastic differential equation remains confined within that ball? Even if I initialize within the ball,
Well, we
and
can assume that well find a local minimum.
no,
And
it's
we
not
can
about
construct
assumption.
the ball.
It's more than that. You have to assume that the whole path remains inside the ball.
Then maybe we can move on. There's a question in the chat, so maybe we can discuss afterwards regarding the strict assumption.
All right. So, belong to the same, I think you mentioned that the local cells belong to the same equivalence class. Am I correctly understanding that they yield the same empirical risk? Are they also equivalent or similar in terms of generalization error? Thank you for this question. And for the first one, yes, they have the same empirical risk. But for the second, the answer is no, because we actually proved that on the loss landscape, the local minimum are equivalent. So the equivalence is in terms of the empirical risk, but for the generalization error is determined by the local geometry, not only the value of the local minimum. Have I answered your question? I think so.
I have a question about your equivalent class. Usually when you use this, you will need to define an equivalent relation first, right? So what is the defined equivalent relation?
Okay, because we actually proved that the local minimum of this model one have a single representation of the global minimum of model two. Because actually all the equations here construct a mapping from some point of this model one to one point of this model two, right? Because
Sorry, because you're talking about quotient space here. If you apply some quotient space, it's just the definition of the equivalent relation you're considering is what is it?
so so if 2 points of model one after all the equations mapping to 1 point of model two.
Okay,
And the 2 points are from one equivalence class.
okay,
Is the definition here.
yeah, thank you.
Yeah, can we go to the peg bias and bounds?
Okay.
Okay. How can we use this? I mean, like if we usually the peg Bayesian bounds, especially like variational inference, we usually use it for the loss functions. But when can we use this? I mean, like RQ is basically a loss function, right? And yeah, using this component, it is like to optimize this function as well and finding the upper bounds, or how is it like similar what like peg based by backpropagation something?
Well, I'm not fully sure about the question. I can repeat your question.
So basically, how to use these loss functions in
Yes.
our neural networks? Is it like just optimizing these functions? Or
Well, it's a very good question to optimize the generalization bounds. So honestly, it's quite difficult to directly optimize this bound because some of terms are quite hard to calculate in practice. But actually, we can optimize some term of this bound, like the determinant of A, and it has been used in another works of myself in neural architecture search. Like we can control the determinant of Hassen to find better neural architecture in search one. And it's like a regularizer actually. And well, I think some other folks in sparsity can be theoretically explained by some of the generalization bounds, not only this one. Well, the Hassen of determinant of A relies on the number of eigenvalues. So from this point, sparsity approach is reasonable, right? And for some other generalization bounds, there are probably some norm of the neural networks, and some norm has been used as a regularizer in training neural networks. But if we hope to directly optimize the generalization bounds, it's sometimes too difficult.
even though we use this Bayesian bounds?
Yes, because here we will have 1 over delta, so it's a high probability bound. It's not an exactly bound. So this bound holds in probability of 1 minus delta, and there is a log n. Even if we fix all of these terms, it actually reduces. It either reduces to the regularizer or too hard to calculate.
Yeah, because like I think some papers also like determine the delta and
Yes,
especially the delta. Delta is like kind of like probability. Right?
yes.
Like the samples are independent.
Yeah, it can be fixed, and there are actually some areas like data dependent calculating or some like developed by Dr. Roy and his lab in University of Toronto, right? But I think that point is to optimize the generalization bound itself, not optimize the neural network via the generalization bound. I hope to optimize the bound in a data-driven way to find a better generalization bound, right? So, and a similar direction is to optimize the initialization distribution via the generalization, via some tag-based bound, right? But I'm not a fan of that idea. It sounds like we have known some information of data and then found a better initialization. So, well, I don't want to make assumption of the data. Make the assumption that we have known the data before we have trained the neural network on the data. But if we have knowledge of data, we can choose a better initialization distribution, right?
Can I ask a related question about VC dimension? You showed us some results about VC dimension in terms of the parameters of the architecture of the network. A question that occurs to me is VC dimension in any way compositional? In other words, can you obtain an estimate for VC dimension of the network in terms of estimates for each layer?
You mean, sorry, then I repeat the question.
Well, I mean, the parameters there apply to the whole network.
Yeah, right.
Is there a way of calculating the VC dimension or an upper bound for the VC dimension of the network in terms of the dimension calculated for each layer, and then combining those estimates layer by layer? Is that possible? Is that how these results
Yes.
are obtained?
Yes, and if I'm not wrong, the work here just use this compositional approach to prove that the upper bound of VC dimension.
Right.
And a disadvantage here is actually, from my opinion, in my opinion, is from the compositional approach, it suggests that if the neural network is deeper, it has worse generalizability.
Yeah.
But this property is not empirically verified. With deeper neural networks sometimes have better generalizability. So the community is actually not in favor of such generalizability that has a negative correlation of the depth.
Right. But I think, well, thank you.
No problem.
I think that's very reasonable points that you make. I think I think it might be that, I mean, the VC dimension that one actually uses in practice is way less than any of these bounds. Because if it was anything like that, you would have zero generalization. It would be impossible to generalize. And everything, you'd be way overfitting. So there must be some argument that gives you what you might call the true, or the experimentally obtained dimension is clearly not the same as these bounds. Would you, if you think that's correct, would you like to speculate as to what the right answer might be instead of these really large formulae?
Well, it's a very good question, and if we hope to, when we talk about true generalization bound, I would say this VC dimensional approach probably has a very true generalization bound. Let's come back to John's experiments. And it's not about VC dimension, but it's about random complexity. Because the complexity actually used the correlation between the neural networks and a random noise to model the complexity, to measure the complexity. So if a hypothesis space can fit in a random noise, it means the hypothesis space is too complex and it needs to have bad generalizability. So this experiment shows that neural networks can have very good can fit in the random noise. So it needs to have a very bad generalizability. But so from this point, empirically, the random complexity is close to the true generalizability. But and we can find some very bad experiments result of deep learning, like such random labels. So my vision is that if we hope to have a worst case generalization bound, it must be very bad. And the VC dimension, the results based on VC dimension and the random complexity are close to such true worst case bound. But but if we have fixed the data, the generalizability is good. So it's a real story of deep learning. If we have a good data set, and if the neural network is trained on the good data set, the data dependent generalization bound, the true data dependent generalization can be quite good. So the vision is not to study the worst case, the universal worst case generalization bound, but study data dependent bound. Come back to the SDE approach. many results are rely on the sharpness or flatness of the local minimum, or relies on the Hessian matrix, or the local geometry of the local minimum. And this local minimum is determined by data and the model. The real story here is just to assume that we have a good data set and then have a generalization problem. It's also the philosophy behind Dan Roy's work.
And you also have the chat question in the chat. I think maybe somebody.
Okay. All the Maruyama formula is dx mu dt plus square root dt times sigma w for w from 0, 1, but it seems that dt is used in place of square dt. Yes, thank you for this question. And well, I would say sigma. I would say there are quite many SDEs are used for modeling the trajectory of SGD, and actually, well, probably we can use this formula, and we probably can use other formula. I probably can talk about some other examples, like they even do not assume that the noise term is from Gaussian distribution, like they are from the wave process by work of Michael Jordan and Peter Basses. So, well, I would say there are quite rich literature in this direction to have different stochastic differential equation. I'm not sure if I answered your question.
Hello?
Yeah.
I gave a question. Yeah, so just a simple question, like, so because I think it should be square dt, because it's a time variable that you at the end of the day you will take the limit of the dt to some point, so that you kind of should be able to recover to the stochastic differential equation. Whereas if you use dt rather than square dt, then you should make the stochastic process of the Brownian motion dependent on the time difference. Then if of course the variance of the Brownian motion is the difference between the 2 points, but yeah, it's just it seems like a non-standard. So I just don't know whether it's some kind of errata, or you have any kind of other insights. Yes.
Well, thank you for this question. And well, if the noise is dependent on the time step, well, I think it's a good point to, and it's actually a more sophisticated model of the trajectory. Well, I would say my model is perfect, and it's actually tracks of the theoretically true model. We just hope to build a model that in some sense is reasonable, and go to find out whether it can have some suggest some insights of the theoretical behavior. Well, I would say if we assume the noise is dependent on the time step, or actually dependent on the exactly time, I would say it's a reasonable assumption. It will be a reasonable assumption, and probably suggest some insights of the behavior.
Okay, thank you. Yeah.
Thank you.
That's it. Let's give you another applause to the speaker.